All right, buddy, this is Mr. Lee. Let's go over the sticky tape labs. This is the sticky tape post lab. All right, let's begin. So from this lab, I'm going to speak about the interactions just as a whole. Okay, I'm not going to specify each individual tape. So the first interaction that you probably saw was the attractive interaction. Okay, attraction. All right, so let's go over that one. Let's call the one on the left 1 and the one on the right number 2. So when you did very certain actions, tape 1 became attracted to tape 2. So what you should be able to do now is come up with a free body diagram for this scenario. All right, so like all good free body diagrams, we're going to start off with a object in the middle. That's that dot. And the very first force that we should draw for this scenario is the force of gravity. Right, so that shouldn't be new. We also had the hand holding up the tape, so we'll call that F1. All right, now the new force, the electrostatic force that we discovered yesterday. So there's going to be a couple of things that I want us to start utilizing when we start naming these forces. And it's the idea that there are two objects for every force. Okay, whereas like the force of gravity, the two objects were the tape and the earth. Right, and we're just used to that, so we're going to skip the naming convention there. But because this is new, let's name this appropriately. So here we have F of E. Okay, so this is the electrostatic force that object 2 has on 1. Okay, and this is for object 1. Okay, object 2 on 1, and object 2 pulls object 1 to the right, and we have that evidence because the tape curves like that. All right, if we were to do the free body diagram for the other object, it will look nearly identical. Okay, so this is object 2, except object 2 gets pulled to the left, and we call that Fe. So this is the electrostatic force of 1 on 2. Now, the reason why I want to showcase this is because one of Newton's laws actually demands that we have this naming convention. This force here and this force here, if we were to just swap around the numbers, it's the same exact thing, right? F of t on 1 and F of 1 on 2. That's Newton's third law. So this is another way to make sure we never forget that these are equal and opposite pairs of laws, right? They have the same magnitude. So that's what attraction looks like. And the other one that you might have saw or you might have seen is the repelling with repulsion. So let's do that. So if this is object 1, okay, almost identical to the attraction, except object 1 is being pushed here to the left. So we can say that is F of E that 2 does on 1. Let's do the same for the other one. Okay, almost identical. But the naming convention is F of E. Okay, this is how object 1 interacts with 2. Once again, we want to get into the habit of doing it this way so that we're good with the naming conventions and so that we're good with Newton's third law shown there. Okay, now the reason behind why this activity worked the way it did. We're going to take a step back and we're going to go back to hopefully some things that you remember from chemistry class. Okay, all matter is composed of atoms, and the atom is composed of 3 subatomic particles. Okay, this is the model of a Bohr atom. Okay, it's not the best model, but it's a model that just helps us understand what's happening on the inside. Okay, inside this is what we call the nucleus. And inside the nucleus we have the positive proton. So positive means that it's proton, and we have an equal sign there, and we're going to use that equal sign to represent the neutron. And this dotted line, that's like that's what we call orbitals, or the pathway that the electron would take. Okay, so you might see me write it like E with a negative sign, or just like a negative like that. So both are acceptable, and this is for the electron. All right, so that's the model of the atom. And in this model, there's a couple of constants that are in your equation sheet that we will be using throughout the year. So let's go over that. First thing here, the proton mass, 1.67 times 10 to the negative 27 kilogram. Okay, it's not massive at all. And it's important to know that the proton's mass and the neutron's mass are identical. Okay, and that does come up later on. Next, let's talk about the electron. Okay, so the electron has a mass of 9.11 times 10 to the negative 31 kilograms. Okay, it is not massive compared to the proton. The proton is more massive. All right, now when we are talking about charge, okay, when we're talking about the charge of the two atoms, we have this number here. I want to point out that this number represents magnitude. Magnitude means that it is just the number, and it can mean positive or negative. So a proton has a positive 1.6 times 10 to the negative 19. An electron has a negative 1.6 times 10 to the negative 19. So the amount of charge that it has is equal to each other. And so at this point, hopefully you're wondering, Mr. Lee, what is a charge, right? So a charge is a property. By the way, charge is property of matter. Okay. Charge is a property of matter, and we represent charge with the letter Q. Okay, and the units for charge is capital C for coulombs. Charge is a property of matter. A lot of people think that charge is like a fluid or like a substance because we often describe charge as flowing, but it's not. It's what is there to help describe the matter itself. Okay, and with that, okay, we can now describe why things interact with each other. So a couple of fundamental rules. Let's see. Matter interacts with each other with imbalance of charge. Okay, so this is just a really fancy way of saying if something is more positive or if something is more negative, it will always interact with other objects. And this is one of the reasons why when you just had those two pieces of paper, I believe, and maybe even two, so this is the paper and this is the foil, okay, they didn't really interact with each other because there was no imbalance of charge. If you're wondering what caused the imbalance, it was the pulling of the tape. When you pull the two tapes apart from each other, it caused an imbalance. But because you didn't do that with the paper and the foil, there was no reason for an imbalance of charge. Therefore, the two objects did not interact with each other. All right. So with this in mind, let's go over the conservation of charge. Conservation of charge. So this is a huge fundamental law that we must always abide by. It's kind of like conservation of energy, conservation of mass, and conservation of momentum. It's very, very important for us. All right, so always define your system. Let's say we have two objects. Let's say we have object 1 and object 2. Okay. Let's say object 1, 2, let's say it has a total of 10 positive coulombs and negative 10 coulombs. Okay, there we go. Object 2, so this is, for object 1, we can call that neutral because it has equal amount of charge. Object 2, let's say there's an imbalance of charge. Let's say object 2, let's say there's positive 10 coulombs. Okay, and we'll say that object 2 has negative 4 coulombs. Yeah. Okay. So because object 2 has more positive charges, we call this positively charged object. That makes sense, right? Okay. So in this scenario here, the two objects would be interacting with each other. And by the way, let's go over the forms of interaction after we do the conservation of charge. Okay, so for the conservation of charge, we need to make sure that all the total number of charges is the same no matter what. We have a total of 20 positive coulombs, okay, in the system, and we had a total of negative 14 coulombs. All right, so let's say we allow the two objects to touch, okay, and the touching part is important. If there is a way for the charges to interact with each other or jump, it will take the opportunity to do so. And the most common way is for them to touch. That's why we had the two pieces of tape on top of each other, and then we ripped them apart. Okay, that allow for the transfer of charge. Also, it's important to know the universe likes things as balanced as possible. Okay, so after you put these two objects together and then you take them apart, so in between here we have object one and here's object two, right? We put them together and we took them apart. Now we can figure out exactly how the charges will redistribute between each other. So here's a rule. Only negative charges move. Okay, the positive charges, they will never ever move. Negative charges are what we call free flowing charges, and positive charges are not. That's because, if you remember from up here, the positive charges are part of the nucleus, and that's the part of the atom that actually makes up the object itself. Okay, and so unless you physically move the object from one object to another, the number of positive charges will not move. So let's start off with that, right? Here we have positive 10 and positive 10, right? Because the two objects, they won't share positive charges. But now we have to distribute the negative charges as equal as possible. So if we take 14 divided by 2, we'll get a total of negative 7. So this object will get negative 7 coulombs, and this object will get negative 7 coulombs. So before, we had an object that was neutral, okay, and a positive charge. But after the two objects interacted, we can see here that this is a positively charged object, and this too is a positively charged object. Okay, and now because we have at least one object that is has an imbalance of charge, we know that they will interact. So let's go over the rules of interaction. Let's go over the repel first. Okay, so repel says like objects always repel, or like charges always repel. So positive on positive, negative on negative. Okay, unlike always attracts. So that will be positive, negative, negative on positive, positive on neutral, and negative on neutral. So we have 4 different combos that you should keep in mind. All right, wonderful. Yeah, in the next video, we are going to go over the different methods of charging and how that affects the different objects. So if you remember from this lab, we had the metal foil and we had the pieces of paper that interacted with the sticky tape. Okay, and it was kind of hard to see because it was so humid. But the foil and the paper didn't interact with the tape by the same magnitude or the same degree. Like there were objects that interacted more or less, and we'll be able to see why. Okay, and that'll be in the future videos. Until then, I will see you next time. Bye bye.